and where are we going, right? I should also start recording. Before we start, are there any questions? So remember that at the end of the class, you can ask any questions. And I have also started my office hours. So yesterday I held office hours and a couple of people did join. So that's always a place where you can come to get your questions addressed, whatever you may have. And I have to admit that I have not contacted the graders yet, but I'm going to do that today. So you should expect first contact, either today or this weekend. Just get in touch with them and they will write to you. Yeah, also I noticed that the number of people who are in the CS stream is exactly 50. So, whether you start reading from the first list and the second list, they can both start reading independently. It doesn't really matter.
Sir, like I had a request, sir. So can you record the like general discussion that we have at the end of the class?
Well, I can, but it's not really clear whether it is profitable or not. Okay, let's see. Okay. Okay, let us see. Let me consider that, because you see, okay, whatever discussion we have at the end of the class, I never sort of take. I'm never going to plan to take it for granted. As in, we will never assume that. We will always start where we officially end the lecture. Right? So, okay, so let's start recording before I go further ahead.
Recording in progress.
Okay, so where are we and where are we headed? So remember our goal. Our goal is to do analysis in multiple variables. So we are largely going to be working in Euclidean spaces. Maybe we will put a different notion of length at times. And for this purpose, we define this notion of non-linear spaces. But really, what we want to do is analyze continuity, differentiation, maximum, minimum, and then in a later course, you will also do integration. So we just want to do calculus that you did in the first semester in one variable, in multiple variables. Right? It's a very concrete goal. But for this purpose, maybe I should not say but, and for this purpose, we have introduced a fair bit of language so far. So we talked about non-linear spaces. And then we are introducing further words. So we talked about metric spaces. And today we will, discuss topology on metric spaces. So there is the language of balls, open balls, then closed sets, open sets. Then we will talk about compactness. Now, the thing is, anytime you introduce new words, it takes up precious real estate in our mind. Okay, and this is something to be, jealously guarded. You should not have, garbage words in your mind unnecessarily. So anytime new definitions are introduced, one really has to justify why it is worthwhile to introduce these definitions. And today, maybe we will give one good answer. In that the notion of continuity, which is a very fundamental notion, that these new words allow us to talk about continuity in a very efficient and simpler way. All right, so that's our goal, topology of metric spaces, and then see what continuity means in this language. So once again, what is a metric space? Let's write it down. Maybe for the last time, but definition. A metric space X is a set X with a distance function D from X cross X to the set of non-negative real numbers such that three properties hold. So let's write them down. The distance function distinguishes distinct points just by whether it is 0 or not. D of then the symmetry property, and the all-important triangle inequality. So dxy plus, so how is that connected with dxz?
Greater than or equal to.
Exactly. Very good. So definitions for x in metric space x and some real number r greater than 0, we have the notion of a ball around x of radius r. This is the set of all points y such that the distance between x and y is strictly less than r. If we replace this with inequality, then we get the notion of a closed ball. But the open balls are more important for us at the moment. Okay, so bunch of definitions. So a set U inside X, it's called open if U is an arbitrary union of balls. Okay, so good. Let's see what this collection of open sets, what properties this collection of open sets has. And there are some very basic properties that I listed at the end of last class, which I hope you did prove. So let's list them. Oh, and before that, so claims. So there was a simple but technical result that we proved last time. Before that, some more words, so definitions. Neighborhood of x in X is what?
So if I remember the definition correctly, it's a set containing an open set in which X is contained.
Correct, exactly. So is such that, and here is the, you should really keep the picture in mind. X in some open set and if n itself is open, then I call it an open neighborhood. The reason to have this, to have this word is that sometimes you want to talk about sets which may themselves not be open, but containing a point X, which themselves may not be open, but contain an open set containing X. In other words, contain a ball around X. Let me justify the in other words. So what was the small result that we proved last time?
If X is in an open set, then there exists an open ball whose center is X, which is a subset.
Exactly. And now, just as a tiny extension of thought, let us just say we saw. And I'm going to write this in word. Any neighborhood, okay, let me not be so lazy. Any neighborhood of X contains a ball centered at X. Just take a moment to think about this. Is it clear? I want everybody to answer this question honestly for themselves. So in terms of the picture, what do we have? We have X. We have some neighborhood, correct? That itself may not be open. But what do we know? We know that there is an open set containing X inside that neighborhood, right? So this is N. And then this is V that is open. This is X. And we saw that inside V, if I have given a point X, then I can put a nice ball around that. Okay. So very good. So properties. So let's write claims. One, any union of open sets is open. So I'm sorry, let's say, okay, so let's write this down. Fix a metric space. Right. So see, every time I talk about open sets, it's understood that there is a metric space along with a metric, and I'm talking with respect to that. Okay. So any union of open sets is open, and is that okay? Because just look at the definition of open set. What it says is that an open set is a union of balls. So if I take a union of such unions, it just becomes a big union. Right? Now, if you want to write this as a formal statement, then we will have to introduce some terminology. Shall we do this? This is not a rhetorical question, okay? Because when it comes to writing things down, you are still at a beginning stage. I said earlier that I would like to not write down every nitty-gritty detail and be pedantic, but that's my preference. If you have to do that in class, and if you think it will be helpful to you, then I'm happy to do that. So I'm looking for some direction here. Shall we write down a proof, a formal proof?
Yeah, yes, sir. Let's do it.
Okay, let's do it. All right. So any union of open sets is open. All right. So what does it mean to take a union of sets? That means that all those sets have to be named, correct? So let us say this. So let's prove. So so V alpha. So what does it mean to take a bunch of sets? You see, taking a union means I have to have a family of sets, but a family of sets is really a set, correct? A family is a set. So I have to have some kind of indexing mechanism. So let V alpha in I be a collection of open sets. Right.
So does theorem take infinite union into consideration?
Yes, absolutely. So that's why this word is there. Any union. So that is the reason why I did not take this index. So that's the reason why I did not call these open sets to be V1, V2, and so on. It could be infinite. But then why did I not name it as V1, V2, V3, dot, 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 dot?
So
it may be
I can also be
uncountable.
uncountable, or
Right. So yeah, sorry. So maybe one person can speak.
There could be uncountably many elements.
Right. So there could be an uncountably many elements in the index set. In other words, the number of open sets that I'm taking could itself be uncountable. Right.
So then how are you taking an index by integers?
Oh, sorry. This I does not mean integers. Integers is universally denoted as Z, the blackboard bold font Z. I is just stands for index. Okay, so let me just write where I is an index set. Now, what does index set mean? It just means something psychological. I is just a set, right? Okay, very good. I mean, if you want to be very formal, what does this mean? It really means that there is a function from the set I to the power set of X. It's an example of saying something which is true but not helpful. Do you see what I'm saying? This is effectively, what do we have? We have some set I, and we have a function from the set I which assigns to each element of I a subset of X. In other words, I have a function from the index set, what I'm calling the index set, to the power set of X. But such that the image of any index alpha is actually an open subset of X, not arbitrary set. Okay. So what do we want to show? Union of alpha in I, V alpha is open in X. Okay, but let's carry on. Since each V alpha is open, V alpha is equal to a union of balls. Now you see the terminology becomes a bit problematic. Okay, so what does that mean? It's a union of balls. That means I have to write a union of balls. Now for each ball, I have to have a center and a distance, correct? So if I just write, let's say C and R, what is this going to be a union over?
So C and R can belong to some kind of arbitrary set that's unique to alpha. Like it can like some set of all the different C and R that made, let's say, tuples of C and R that you're considering.
Right. Now you see, every time I say a tuple, I have to be careful, because usually when we use the word tuple, we mean finite. Whereas this itself again need not be a finite thing, right? So you see, for each V alpha, I have a union of balls, but that union indexes over, it's a family of balls, right? So that means I have to have an indexing set even for that. What shall I call this indexing set? Just like the first union, it's alpha. Okay, by the way, I really want to say something. For those people who are sort of, who think, what's the point here, right? What are you even talking about? Isn't this completely obvious? I hear you, even if you're silent. And you're absolutely right. What is going on is pure pedantry. Okay. So if you're impatient with this, you can see this as an exercise in notation. That's all. Really what we're saying is that a union of sets is still a big union. All right. But anyway, so what should be my indexing family over here? I need some notation, right?
So maybe you could call it I sub alpha or something.
Right. So correct. So you see, this indexing set also has to be something that is tuned to alpha. So I need to have a notation. Now, I sub alpha, there is nothing wrong with having I sub alpha, but that's psychologically bad. Okay. So let's use a different notation over here. So let us call this family some J sub alpha. Okay. And now I'm indexing over this J sub alpha, right? So that means I have to take another variable. So what shall I call this? I have to give a name to this index. See, look at the first union. It is union over alpha, union over index set I, but I took for every alpha in I took the set V alpha and I took their unions. So here also I have to do some device like that, right?
No, so what I just said in the beginning is that if J alpha, like J sub alpha is like a set of tuples CR, like two tuples CR, right? Then you can just say that CR, like, like parenthesis CR belongs to J alpha. If that's how you define the set.
So now see, you want to tie the C and R with the notation.
Yes, sir, right. Yeah.
Confusing. How about just the following? Let's make a variable. See, remember, when you have a set, when you list elements in a set, and by list, I do not mean denumerable, right? When you have this curly brace notation, how do you define a set? Define X such that X satisfies some properties or whatever, right? That X is a name over there. So we are just using a name for every beta in J alpha. I have a union of balls that is indexed by beta. So what I can do is I can I'm going to do the same thing that you were saying, but for every index beta, I have a ball, right?
Right. Yeah.
But that means that for every beta, I have a ball, and a ball needs to have a center and a radius. So I'm simply going to say, sorry, my notation for the ball, I should be careful with. Subscript. So this is R beta, C beta. Remember, that's what an open set has to be, right? It's a union of balls. Now I'm taking index over, I'm taking this union over an index set beta. That means for every index, I have to have a ball. That means I have to have for every index element beta, I have to have a center, which I'm going to call C beta. And I'm going to, and I need to have a radius, which I'm going to call R beta. So,
Sir, a small question, sir.
yes.
I think later on, I think we would not need the specific center and radius for each ball. So might it be like simpler to just have a set consisting of all the balls and just take a union over the set? So beta could just refer to, so J alpha could be a collection of open balls, and beta could just refer to an element of the set, and we take a union over beta.
Right. So, okay. So you do not want to give a name.
I did not want.
No. So what you are saying is that, okay. So this is what. Okay, so I'll just write down. So. But this becomes a bit circular. You see, how are you going to? What is your index set?
So my set is some J alpha, but now J alpha, the elements there are open balls.
Which open balls?
Do I need to specify?
Yes, because if you're going to tell me, if you're going to taking union of a family of sets, you have to first tell me which family. You see, it becomes circular over here. So what you want to say is that so okay, so I'm just going to write this down. You want to take a collection of the sets B, C, R, right? Remember, this is not the union. This is the names of the balls.
Yes, sir.
This is what you want to do.
Yes, sir. And
right.
Yeah.
But what is that family? You have not specified the family, correct?
Sir, but that family is given to exist because
right.
V alpha is open.
Right, V alpha is open, so that family is given to us. So see, what you are saying is that you do not want me to take a name. Just fine, all right. So
I guess I was asking whether it would be simpler and whether it would be valid still.
Okay. So now the question of, so there are two separate questions here, simpler and valid. Now, often simple or not is really in the eye of the beholder. You know, what is transparent to one person or what is easier or more natural for one person may or may not be the same for others. Now, whether it is valid or not, okay, so maybe even the following. Okay, so perhaps make it union over so union over the given family of balls whose union is V alpha of those balls. That's really what you want to say in words, right?
Yes, sir. Yeah.
Okay. So let's not quibble about this. Okay.
Yes, sir.
I just want to sort of get through this. No mathematics is happening over here. It's pure pedantry.
Yes, sir. Yeah.
Yeah. Okay. So then I'm sort of regretting getting it down, going down this. Oops, sorry, that's a poor choice of letter over there, because B and beta could look the same if I'm not careful. So B R beta, and this is the point which is still a union of. If you want to be even more pedantic, then maybe I have to make an index, because this is a union inside a union, right? So maybe now I have to make now a separate index set, which is the disjoint union of all the J alphas, correct?
Yeah.
Heck, if I do this, then this is the union of beta inside the disjoint union of all the J alphas of the respective balls. Which is still a union of balls. Okay. So I'm really going to write this over here, because okay. All right, so I think we should now banish this and actually do some maths. Okay. So the thing is, yeah, okay, so if V1 and V2 are open, implies V1 intersection V2 is open. This is more interesting, and actually there is some content in here. So what is this saying? That intersection of two open sets is open, and therefore, just a copy, and therefore intersection of a finite number of open sets is open. If you like, by what? So how do I show that intersection of three open sets, V1, V2, and V3 is open, given this result?
So we can induct, like we'll view intersection of two sets as one set and apply the result for.
Yeah. So if you like, by induction on the number of sets, if you like. So there is actually some content here. So how do I do this? And now let me not. So here's the picture. The picture. So this is V1. Let's not draw it as a circle. Or okay, might as well, really. So what does it mean to show that a set is open? That means that I have to show that it is a union of balls. Correct? So we will prove. So you see, here's the picture, sort of, and I want to go back to this claim, the earlier claim, the we saw part of this. Correct? What this is telling you is that the way you sort of visualize open sets is, don't look at it aggregate, look at it locally. What this is saying is that if you are anywhere inside an open set, you have you take any point inside the open set, then there is some small wiggle room around it. That's what this is saying, right? Pick any point inside an open set, you can put a small ball around it, so you can wiggle around that point. Now, the wiggle room that you have, you may not have as much wiggle room as you would like. So if you imagine this, let's just say you take an open ball itself as an open set. And if you take a point which is close to its boundary, the word boundary I'm here using in a non-technical sense. All right, I have not defined what the boundary of a set is. But look inside the plane. So there is the circle using the Euclidean norm. So if you look at the points that are exactly at distance which is equal to the radius, then they are not in the open set. So you take a point which is just slightly less than that. It's very close to that boundary. But nonetheless, you can take its distance from the boundary and take something small and something smaller than that. And you will have that much wiggle room around the point. And what I said now is essentially the proof of the we saw claim that I have written over here. So that's the picture of an open set to keep in mind, that whatever point you take inside that open set, you have small wiggle room around that. So what we say is that openness is a local property. There are many properties of topological nature that you see are local properties. This is the first one. The definition of an open set itself is a local property. Okay, so what we want to show so what do we want to show? So one way of showing that a set is open is say that, okay, take any point in this set and I want to show that it is inside some ball, correct? Which is totally contained in that open set, because this set is supposed to be a union of balls. So that means the point that I have taken must be inside one of those balls. But now I get to say that if the set is to be open, then actually I must be able to fit a ball around X that point. That's a necessary condition. So this is my proof strategy, that if I want to show that a certain set is open, one way of doing that is to try to ball around that point inside the given set. Okay, so I hope this is clear. This is not a requirement from the definition of open set. But by the very first claim we saw, this turns out to be a necessary condition. So, okay. So we will do this by showing that for each X in the set that I'm claiming to be open, there exists R greater than 0, of course, such that there is a ball of radius X inside V1 intersection V2. Okay, so let's draw a picture and let's start looking outward from X. So let's get rid of this. And there is this point X, correct? Which is in the intersection. That means that it is in the set both V1 and V2. So there is V1 something, and then there is V2 here, right? Okay. So my picture, really this part I should be, just for the sake of drawing, I should have a little more room over here. Okay. So this is V1 and this is V2. Now, what does it mean that the point X is inside V1? It means that it is contained in a ball inside V1. But we know actually that I can put a circle where it's totally around, totally inside V1. Okay, so you know what? Okay, so here is okay, so let me just erase all of this. Let's try to use color. So there is that point X. Let's use red for this is one open set around this point. Now, what does it mean that the point X is inside this open set? We saw that that means I can put a ball around this point, which is totally inside this. Okay, so this is V1. Now let's draw V2. So this is V2. Okay, so what does it mean that what does it mean that this point X is inside V2? By virtue of being inside an open set, that means that I can put a blue circle that is centered at X and which is totally inside the blue part. Okay, so now I again did something bad over here. I mean, there is nothing wrong, but okay, I think we are okay. So I'm just going to draw a blue circle. Now, unfortunately, what has happened is that the blue circle is totally inside the red circle. But does that necessarily have to be the case always?
So one of the circle balls will always be in one of the.
Yes, and you tell me why.
So like the minimum one will
Exactly.
be. Yes.
Exactly. Now you see, this is where the fact that the point was, this is where the fact that I took balls that were centered at X was really useful. Imagine that if I had taken a ball that was a red ball totally inside the red set and a blue ball that was totally inside the blue set and X was only in their intersection. If that were the case, the two circles need not have intersected with each other. Do you see this? However, because both the circles are centered at X, one of them has to be contained inside the other, or both of them will have to be the same, right? And whichever is the smaller circle, now that is contained in both the sets, right? Both the red and the blue open sets that I took it at the beginning. So you see the earlier claim that I had over here, the we saw part. Sorry, where is that? The we saw part, that is a useful little thing. And I used it over here. Okay, so let's finish writing the proof. Okay, their exists are such that, okay, so as X is inside V1 by yesterday's claim, yesterday's claim, there exists, let us say R1 such that X is inside B, R1X, which is inside V1. Similarly, X is inside B, R2X, which is inside V2. Now what do? Take R to be the minimum of R1 and R2. Then we have X is in B, ball of radius R, which is inside V1 intersection V2. Okay, so any questions on this proof or anything else? All right, so I wrote down all the details, but with time, things of this type, I would like to be able to leave to you more and more, okay?
So
this is a straightforward argument, sort of follow your nose kind of argument. Yes, go ahead, please.
So in this proof, we don't need to add anything else, like because R is less than equal to R1 and R2, therefore the ball will be contained in both.
Right. Okay. So now you see, do we need to add anything more? So the question is, who is the audience? So because B R or let's use completely different letters. B SX inside B TX when S is less than T. This is what you're saying, right?
Yes, a sort of something.
Right? But you look at the definition of the ball. I mean, it is a valid thing to point out. So let us point it out once. What is the definition of a ball of certain radius? It is the set of all points that are at a distance less than, so the first ball is the set of all y such that the distance between x and y is less than s. Well, if some number is less than s, then it is also going to be less than t, because t is bigger than s. So just to make it completely and utterly clear. But coming back to the point, how much do you write in the proof? And the answer to this question is very context dependent. Who is writing? For whom they are writing? What is the purpose for which they are writing? All of those things are very important, right? In your humanities or English classes, this must be discussed, but it is true even otherwise. If you are a student who's writing this in an exam to be graded, then maybe you do want to go a little extra and write all the justifications. But let's say you're a researcher who's writing for other researchers, then perhaps this entire proof will can often be just said, okay, omitted, or proof is left to the reader, or it is clear that, right? But I advise you not to take such an approach at this stage in your career. And I sort of gave you two extreme examples, but there are lots of things in between, right? So how much detail you want to give really depends on the context. Now, in this the key thing in this course is the key thing in this proof is really this sentence, right? This idea. That's what the proof is turning on. And before that, you're setting the scene by taking the ball centered at that point. But the reason to do that is finally to do this maneuver by taking the minimum of the two radii. So really, a one sentence version of this proof would be to say, put a ball around X inside each open set and take smaller of the two balls. So one sentence version of the proof. Okay, anything else? Right, so let me say one more thing. So how do you decide how much to write? The point is, you should write enough so that whatever is written based on that, the argument is completely obvious to you. And next, just by reading whatever you have written, somebody who is just slightly behind you, let us say that you're using a certain amount of knowledge, let's say up until this lecture, and you're asked to write some proof. You should write the proof in such a way that the person who has not attended this lecture but knows all the words that are required in the proof should be able to follow the proof. So when you write a solution for a certain problem, imagine a student who is taking the course after you. Your solution should make the answer completely transparent to the other person. All right, so but let's get on with mathematics. So finite intersection of open sets is open. So then we also have 1' and 2', which is any intersection of closed sets is closed, and finite union of closed sets is closed. So recall, closed set just means complement of an open set. So I hope that both of these are completely obvious. It's just set theory. So I'm going to leave this. So shall we maybe do one of these? Or can I leave this for you? I would like to leave this for you.
Yes, sir, you can leave it to us.
Okay. All right. So let's make this definition. Just to have it, we will not go very far in this direction. A topological space X a topological space is a set X together with a collection of subsets of X. So pedantically, E, a subset of the power set of X. I mean, it's weird, no? Sometimes we use the word set, sometimes we use the word collection. But really, it's just all sets. Set theory. Subset of the power set of X that is closed under taking arbitrary unions. The word arbitrary is superfluous. The word arbitrary is really just for psychological purposes. If I say unions, that means arbitrary unions. Take arbitrary unions and finite intersections. In other words, the properties 1 and 2, I turn them on their head and I say that any collection of subsets of a given set forms a topology on that set. So this collection is called okay. So we will not go too much in this direction, but just this definition I want to put out there. A small, again, technical point of logic. So earlier we saw that the empty set and the whole set are open. Does that follow from this definition? Suppose I have a topological space X under given some topology. Is it automatic that the entire set is open and that the empty set is open?
I don't think so. I think we could just take the empty set to be X.
But okay, so you see here it's it's again a slight point of logic over here. What does it mean to take union? That means it's a collection of sets, and that it's an index set, that it's a set of sets, and I am taking union or intersection over this set. Okay, so the index set is allowed to be anything for union, and it's allowed to be any finite set for intersection. Correct. So if I take union of the empty collection of sets, what is that union? In other words, when the index set is empty.
Yeah, that is fine, right?
Right. So notice, okay, so I'm just going to write this. So union of, so let's say union of alpha in I, S alpha, is the set of all x such that x is in some S alpha. So even more pedantically, let us say x such that there exists alpha such that x is in S alpha, right? Now apply this definition when I is the empty set. And where are these elements x coming from? Everything is in S alpha is a family of subsets of x, right? Now, if I take this I to be the empty family, then that means I'm taking all elements of capital X that belong to at least one of the S alphas. But there are no S alphas. So what is this? So if I is the empty family, if I is equal to phi, okay. Is this clear? I hope that this is okay, because no element of the set satisfies the property that it is in one of the S alphas, because there are no S alphas, right? But now the life becomes a little more interesting if I take the intersection. So what is this by definition? This really is the definition. So what is the intersection? How does so it is the set of those x in X such that
So the x is an element of S alpha for all alpha.
yeah. So there exists alpha changes to for all alpha, x belongs to S alpha, right? Now here is a thing for you. If I is the empty family, what is this?
So this is the entire space because the for all condition is vacuously true.
Exactly, right? Answer X, because the for all alpha condition. So for all alpha, for all alpha where I should really, so for all alpha in I, there exists alpha in I, sorry. I'm doing this on the fly over here. So for all alpha in I condition is vacuously true. For each x in X. Okay. So if I understand this arbitrary union and finite intersection properly, then it's just a comment.
So how exactly is this working? Like, you're saying that there is no alpha, and so
Correct.
X is in S alpha. Like there is no S alpha also, right? So how is X in S alpha?
Because for all alpha in I want to verify some condition, correct? But for how many alphas do I have to verify this condition?
None.
None. So there is nothing to verify. That's what the vacuously true, that's what the vacuous means here. It is irrelevant. Whatever is afterwards is irrelevant. The condition says that I have to verify something for each alpha in I. There are no alphas in I. So there is nothing to verify.
Okay, yeah.
Right. So again, this is just a small point of logic. The first time one comes up against this, it can be slightly disconcerting. but it's true. And another thing is that when you're doing mathematics when you're learning new language or learning some new kind of mathematical object, or just getting used to mathematics done in the fashion the way we are doing, in the beginning, it pays just to look at the definitions, and whatever is required to be proven, just write it down. Just write down statements carefully, what is given and what is required to be proven. But make your sentences completely precise. At the initial level, you will see that a lot of mathematics is just only translation. And translation not even in a particularly deep way, because you could say that, well, all mathematics is tautology that way, right? Because it's just logic. But at the beginning, you don't even have to travel very far. Just write down good sentences. Whatever your confusion is, you try to make your questions precise. And many times you will see that the answer to your question will be either entirely given or at least half given just when you write things down precisely. Force yourself to do that. Okay, but let's get a move on. So one point that is, note carefully. If S is a subset of a metric space X, then S itself is a metric space. And as such, has open, closed sets as subsets of the metric space S. So the question is, is there any connection between being open, respectively closed? Okay, let me not, this kind of construction can be misleading. So being open in X and being open in S. And similar question for closed. Okay. So let's just take a look at this. What are balls? So answer, notice if I want to, so okay, so let's take a point in, X, in S. So let us say for X in S, and let's do this in words. Ball of radius R around X in S, and ball of radius R around X in X. Is there any connection between these? Just look at the definition. There's nothing difficult going on over here. So what does the first thing say? It says take all points in S that are at distance at most r from X. And then the next one says take all points in X that are at such a distance. But the distances are the same. So how do you obtain the ball in S from the ball in X?
take the intersection with S.
Exactly. So as a result, notice what happens. What is an open set in X? It's a union of the balls, right? But what is an, okay, so that is in X, but what is an open set in S? It's a union of balls in S. But each one of those, so, okay, so let's therefore open set in S is equal to union of balls in S, which is the union of balls in X intersection S. But what is that? You know, whatever your set theory, the union distributes, correct? So what do I get? Union of balls in X, and then all of that intersected with S. I mean, strictly speaking, I have to distribute, but you see the second part is just S. Do you follow what I'm saying? Is this clear? This is only set theory. There is nothing happening over here. That S can just be taken out, no? Okay, so I'm not sure if I follow the you know, I don't quite like the quality of that silence. So let's just do this. It really is saying that if I have A1 intersection B union with A2 intersection B. Oh, the B is a bad letter because there are no, some totally different thing. It's not X. Let's say Z. What is that?
A1 union A2 whole intersection with Z.
A1 union A2 whole intersection Z. There is, and what works for two sets, it will work for an arbitrary family. So there is nothing going on. But what have we therefore found out? An open set in S is the same thing as what? A union of balls in X intersected with S. But a union of balls in X is precisely
Open set in X.
So open So this is the upshot. So what we see is the following. So what we saw is that if a set is open in S, then it is the intersection of an open set in X with S. Is the converse true? Just use the same set theory in the opposite direction. If I have an open set in X, then it's the union of balls in S. And now take the intersection inside. So thus, in S are precisely open sets in X intersected with S. Okay. What about closed sets? So let's call this. So this is proper. So this is number 3 prime. Closed set. So let's write this as a claim. A subset T of S is closed in S if and only if T is equal to some closed set of X intersected with S. Again, the proof of this is going to be entirely set theory. So I'm going to leave this as an exercise. This allows us to answer a question from yesterday. So suppose I have an open set of a metric space. And if I take an open set of that, so S is open in X and T is open in S. What does that tell us? That means T is of the form what? T has to equal an open set of S intersection some open set of X. That's what it means. No? But what do I know about such sets? Because S itself is open, intersection of any open set with S will be open in X, right? So upshot, corollary. If S is open in X, then a subset T of S is open in S if and only if T is open in X. Oh, okay, sorry. This is, sorry, that was really bad. What I mean is the exact same statement is true.
Sir, the definition of closed in S, the complement should be open, right?
Right. So definition of closed in, right. So what does closed in S mean? It means that the complement of that set in S is open in S. Okay, so now the set theory gets slightly, I mean, you have to manage this, but you will see that nothing very difficult is going on over here. So that's why this is an exercise. You have to do a little bit of work. But you're right. The definition of a closed set in S is with respect to whatever is open in S.
Okay, sir.
Okay, so let me end with exercises because we are out of, no, we actually have a little bit of time. That's very good. So this is an exercise. Exercise. Same statement. If all three words open. Remember, it's in three places, right? Open, open, open. If all three open are changed to. So the slogan is open set of an open set is open. Open subset of an open set is open in the whole space. And closed subset of a closed set is also closed in the whole space. So just fun and games. Really nothing much is going on over here, but it's useful to develop some intuition. Exercise. For any subset S of a topological space. So it need not be a metric space. It is just some topological space. Define a collection of, not define. Sentence is not coming out right. I want to make S also a topological space. Now, can I really use the definition of what I did in the metric space? And the answer is no, because I don't really have the notion of a distance, no, of distance, correct? But there is something that we have done that tells us how to define a topology on S. And that is, I use the property number 3 that I have proved as a guide and take this as a definition. Okay, so the collection S intersection U open in X defines a topology on X. Defines a topology on S, which is called the subspace topology. Okay, so you will see, you will go much further in this direction in your topology course. But since we are talking about this, it really is not very different. So this is the exercise that I'd like you to do. Okay, so we draw a line over here. So next, we have to do limit points of a subset closure of a subset S and then continuity in terms of the topology. So I really would have liked to get to the final one, but we took some time off to do various things. So no matter. So this is what we will continue with on Monday. But please do try to read about these things so that we can go a bit quicker in class. Okay, so let's stop with this for today.
Recording stopped.
Yeah, and so, I would like to have some kind of direction from the class because, we need to pace this right. I do not want to go too fast and then lose several of you. I'm certain that we are not going too fast. Okay, this pace, from my point of view, the pace at which we are going is a little slow. If we can go a bit faster, then I need to have this. Then I need to get some feedback from you to this effect. Because if I'm just boring everyone, see, if you're in a class, then I can see everybody's face, so I can sort of adjust. I can calibrate accordingly. But here, I don't really know what's going on. If you think that we can go a bit faster, then please let me know. Can we go a bit faster? Maybe what I should do is here. What you can do is, if you have any particular opinion on this, you can send this to me as a private message. If you do not want to, speak out aloud. But I really do need to have some indication from you, because the course, finally has to be useful to you. So. So I could conduct a poll right now. Okay, let us see. Let me see. So, right, polls. All right, so maybe you can walk me through this. And Yeah, in fact, this is nice. Set V. Then there exists R greater than 0 such that X is contained in this ball, of course. BRX side V. Is this the one that you're talking about?
Yes, sir.
Okay, all right. Yeah, so let us see how the proof went. So this is some open set U. This is some X. And then?
We considered another some circle center at U with radius R, which contained X.
Correct. So that was the point, that the V doesn't really matter. The set is open. What does it mean for the set V to be open? That V is a union of balls and X is in V, right?
Yes.
That means that X is in one of those balls. So as V is equal to union of balls and X is in V, X must be in one of these, that is these balls. Okay, so that is certainly correct. So there is some ball like that. Okay. So what was your question?
No, the thing is, I understand the proof. The thing is, why do we need to consider this U-centered ball? Because what if we just
sorry.
boundary defined.
Sorry, just 1 second. Now my picture is very bad. The picture that I have drawn here is of the conclusion that I have. So yeah, I'm sorry. So I should really, yeah, okay. Yeah. So what this is saying is that X is in just one of these balls, right? Okay. Sorry, go ahead with your question.
Yes, now we can just, like you said, we can choose the radius to be less than D minus R and draw a circle centered at X.
Right.
That's fine, but the thing is, why do we need to consider this? Why can't we just take the minimum distance from X, the boundary, or is it because we haven't defined explicitly what boundary is?
Okay, so what you want to say is the following. So idea. Try to take R to be what?
R is less than the minimum distance from X to the boundary of X.
Minimum of, so minimum, okay, so let's first just write this down in words. Minimum distance from,
or maybe the infimum.
X. Right, okay, infimum. So what you're saying is that there may not be a minimum.
Yes.
Right. So okay, so let's say infimum. All right, okay.
So, but then we will have to show that the infimum is greater than 0.
Right. Infimum of distance from X to boundary of B. Okay. So there are several problems here. So one is
sure, I meant the metric space.
Sorry, no. So from infimum of distance from X to
boundary of the metric space.
But what does it mean, the boundary of the metric space?
What I said, like it's because we didn't define the boundary. So,
but okay.
We in any way define. So this is basically the doubt. So can we?
But no. Okay, one second. So now there is minimum to the boundary. So boundary of what? That's also is a question. But so let's first discuss that as an idea itself. Okay. So here is, let's say suppose the metric space is R2.
Okay. Yes, I get it.
Then what is the infimum of the bound to the distance to the boundary? What is the boundary?
Yes, I get it.
Okay, but okay, so that is one problem. But let us suppose that the metric space is not all of R2, but it is some rectangular box, large rectangular box like that. Let us say that is X.
So in that case, can we take the boundary distance to be like at infinity or something like that? So anything.
No, but one second. Even here there is, see, if I take the boundary to, then just see in the picture what distance I am taking. That means you are taking the minimum distance from X to minimum distance from X to a point on the edge of this rectangle.
Yes.
But will that work? Look at the conclusion that I want. I want this ball with radius R centered at X to be contained inside V.
Okay.
Right.
So bound. Okay. So maybe boundary of V. What if?
Okay. All right. So now now we are making progress. So it's not the boundary of X, but it's the boundary of V. Okay. So now comes the next question. What do you mean by the boundary of V?
So
I mean, this is an idea, right? So what you have is an idea. So let's
so like the way we defined norm as distance. So
okay, but in order to have distance, you have to have 2 points. So what are those points?
Point is a variable point on if in any way a boundary of V is defined. That's the question.
Yeah, but now you see, I have to define the boundary, correct?
So is it not defined? Like in any way, is it not possible to define?
Right. We are going to define boundary, but
okay, sir.
Right. Yeah. So we are going to use limit point, where we will have the definition of limit points. So yeah, there is some notion of boundary of a set. Yes. But okay, so let's go a bit further in this. See, an arbitrary open set is something that I don't really know. Right. Remember, open sets are things that we should think of locally. Right. At least now, until we have maybe some characterization of open sets. In a general open set can be quite a complicated object, but locally, if I'm anywhere inside, I have wiggle room. So why not use the definition of, see, whatever you do, if you do not use the definition of what an open set is, you're going to have a hard time proving any result.
Yes.
Okay. So maybe we can now make a more instead of taking the boundary of V, we know that because X is inside V, there is that ball, right? Some ball that X is contained in.
Yes.
So perhaps instead of V, can we choose the boundary of
the ball which contains X?
Right. And now you see, since you know what a ball is, perhaps you can define what the boundary of that ball is. What should we define as the boundary of a ball?
Where distance from X to the point, variable point is R.
Yeah, but what is that variable point? You first have to decide what points you are considering. So what should be what?
So the set of all points which are exactly R distance away from the center.
Correct. So a reasonable idea. So reasonable definition. Boundary of V. So let's say, so far I don't have, so okay, let's just make some, so B D some point C, okay, is equal to all X in X such that, or let's say Y in X such that the distance from C to Y is exactly equal to D. Oh, shoot, okay. That is a bad idea to use use the letter D both for the poor choice of notation. So let's call it delta or something like that. Delta. At least we have a definition, correct?
Yes.
Okay, so there is a comment over here by Srijan, so you can read that comment. We will come to things thinking of this kind later. So boundary. Okay, so all right. So suppose we have we have some ideas that we are exploring. Now what next?
So since we can say, so V is a union of balls, so maybe union of the boundaries of balls in some way.
No. Okay, let's look. Okay. You still are trying to define the boundary of V.
Okay.
Now the question is that something that we want for our purpose? That's certainly a reasonable question to ask. The point is it required for our purpose here?
Okay, maybe we'll see that later.
Right. And also consider the proposal that you just had. That's a problematic proposal, because if you take the union of the boundaries of all balls inside V, you will get lots and lots of points that reasonably speaking, we should not consider as boundary of.
Yes.
Right. Because you see, in the picture that I have drawn here, the boundary of that ball, that circle, the points on the circle itself, they should not be considered boundary of V, right?
Yes.
So it has to be some other approach. But that's not what we want for it's not really relevant for us now.
Okay, I get it.
You already have a certain idea. So let us try to push through with this idea. Now you have a well-defined thing. You have this ball has some center C. I don't remember what the terminology was last time, but it doesn't matter. This, or I think we called it U last time. No, I don't recall what we had. And we have a set of points that is considered the boundary. So if I want to take the infimum of all the distances from X to the boundary of B. Okay. Do you see any problems with this approach? What are the next questions to answer?
Hello, sir.
Yes.
Sir, we should, whatever minimum distance we get, we should ensure that it is non-zero, right? Greater than zero.
Yes. So this is one thing, that this infimum, I should check that this infimum should be greater than zero. Okay. But after that, we still have to show that if I take such a radius, then the claimed statements should still be true, right? I still have to show that all of this is contained inside the ball. Okay, maybe we can do that. But I have problems even before that. You are taking infimum of a certain set of real numbers. What is the very first question to ask?
It should be bounded for the. Okay, it will be bounded. Yes.
Well, these are all distances. So it's going to be bounded certainly by zero. But the point is, we want this to be positive. But even more, you are taking infimum of a certain set of real numbers. The very first question that you should ask, even before, is whether this set is non-empty. Why should this set be non-empty?
In fact, as it is in an open set, X is we are considering X to be in the open ball B.
Right.
So that means it is contained in it, right?
Yes.
And so the distance between 2 points is always there. But the boundary of B is always defined then.
It's defined, but how do you, but look at the definition of the boundary. It is all those points that are distance exactly exactly
Oh,
equal to
okay.
the, right?
Yes, sir.
And in fact, if you just think about it for a moment, I can construct an example where the boundary is empty.
Yes, sir. If we consider the B to be the set itself.
Exactly. If I just take X to be B itself, nothing is stopping me from that. Every subset of a metric space is a metric space. So no boundary. Okay, so this did not work. But I want to say several things. This is exactly how mathematics is done. You try various ideas. Hence, maybe something works, something does not work. This maybe tells you that, okay, what does this tell you? But you see, so this was a failed attempt. So one can now try various things. Can say, okay, still there are several interesting questions that came up, right? Can we do, so we would like to have some notion of a boundary of something. So that's an interesting question in itself. Is there a meaningful way to define the boundary of something, of some set in a metric space? Second, even if I defined it, then is that a reasonable way to try to solve this problem? In other words, okay, we have an idea. The idea did not work, or at least we were not able to make it work. Then can we modify the idea in some way that it works? Not clear to me, by the way. I'm not saying that there is an answer. Think about it. But a short answer to your question, if I were to say, is that the proof that we gave is really so simple that it is the natural proof. Now, it may not be natural to you, but observe. What did we do? We really just followed our nose, correct? So what I have written next to this rectangle, that is just following the nose. That X is contained inside a ball. Now, you see, V has completely disappeared from the picture. No matter what proof we do, we can afford to ignore V completely, because for all I know, B itself could be V, right? Whatever proof I have, it should work even when V is equal, when V is equal to V. So I might as well say that X is in a ball. So what are we saying now? If X is in a ball, then I can put a ball around X that is inside the ball. Even, okay, so, all right. So, see, the point is, at this stage, if you look at the picture, what's happening is that how big a circle I can put around X is going to depend on what? And we used one idea, you're trying to use another idea. What you are saying is that the circle that I put around X depends on how far X is from the boundary. However you think of the boundary. But we had difficulty thinking of what the boundary is. So the other thing is, yes, it depends on how far X is from the center. That's the point that we have. So why not use it?
Yes, I see. It's much more natural and simple.
Correct. No, I mean, but you see, what I'm offering here is that by the way, you're not obliged to agree just because I'm the teacher or anything like that. It's not, because the word natural is very user dependent, you see. It's not a mathematical word. At least the way we are using it, it's not a mathematical word. If you do category theory, then the word natural can be given a definition, but then it's a technical word. What is natural to one person need not be natural for another. But I do want to say that you can try to educate your brain to reach a place where you start thinking of this as natural. Why make more data or introduce more terminology unless it is needed? We already have the given point X, we already have the ball, we have its center, we have the radius of that ball. If we can make do with this, why not make do with this? Again, I mean, this is not a proof. What I'm offering is not a proof. I'm just offering a some kind of trying to be persuasive here. Is that from my point of view, if we can make do with the information that is given, why introduce extra baggage or extra notation unless it is required? So generally for proof, see, a lot of it, and when we are operating with at the topological level, a lot of it is just set theory. So when you're doing set theory, you're saying that, okay, where two sets are equal, what do? You follow your nose. You take an arbitrary point in one set, you name it, you use the definition of that set, you use the defining property of the other set and show that one defining property implies the other defining property. And then you have to do the other way, right? That's how we show that sets are equal, that each one is a subset of the other. Likewise, any kind of two ways implication that something is equivalent to something, you take there are certain sentences just by the shape of what is required to be, what is stated, just by the shape of what is there and what terms are involved in there, you get to write some sentences for free and make some terminology. Generally, you should make this terminology and follow your nose and see where it leads you. At this stage in mathematics, this itself will lead you to a certain stage.
Hello,
Okay.
sir.
Yes.
Sir, I was having one confusion that when we say that a set is open, we actually define it as an arbitrary collection of open balls, right?
So, not an arbitrary collection. Just one second. So you're right. We start with an arbitrary collection of open balls, but then we take their union. Yes, go ahead now.
Yes, sir. So, I mean, from the very definition, if we have an element in an open set, then we can say that it belongs to some open ball.
Absolutely. Right? Yes, absolutely.
And from that, we actually prove that from this characterization, we can prove that around that point, we can draw, I mean, we have an open ball centered at that point, which is completely contained in the open set. So, I mean, which is the very theorem that we were speaking of.
Yes, exactly.
So, I mean, are these two characterizations equivalent?
Just check. Just check. Right. So first characterization is the definition that you gave. And now, what is the second characterization? Formulate it, and then you will see that. I don't know.
Yes, sir. I mean, if we have a set such that around all its points we can draw. I mean, we have open balls centered around that point contained in that set. Then we can define that very ball to be the open ball as per our previous definition.
Right. So
as it contains the center.
Correct. Exactly. So let me repeat what you just said, and this is a very useful way. So thank you for doing this. This is what I was trying to do. What does it mean? Wiggle room around every point, right? So see the definition of, because of triangle inequality, the open sets are something more than the definition gives me. What it says is that an open set is such that, I'm just going to repeat what you said. An open set is one such that around every one of its points, I can take an open ball centered at that point, which is contained in the set. So let's write this down. So upshot. V is open if and only if V is equal to union of X in V strictly speaking, this R, okay, where R greater than 0, well, it always is greater than 0 because where R depends on, I mean, that is important, right? This is exactly what you said, right?
Yes, sir.
And notice the key thing over here is that the union is not over just some set of X. The union is over every point in V.
Yes, sir.
That's the key thing. It's by the way, this is a very small point, but it's a useful point because whenever I want to do something or the other with open sets, and if
Yes,
I
sir.
want to
In the
do
proof
something
of the intersection of two
Exactly.
open sets is open, we used this characterization. That's why I asked it.
Exactly so. All right. So if there is nothing else, then let's stop for today, and then we will continue on Monday.
Sir.
Yes.
So I think that the intersection of empty family is not defined in set theory. Like,
Right. So that brings a very good point. The point is, in a set theory, you have to have a universe. Okay. So now we are really getting into set theory. But you see, in order, set theory has to avoid paradoxes, right? It has to avoid Russell's paradox.
yes, sir.
Right. So, so the ways of doing set theory, there are many ways of doing set theory, and I know very, very little about this. But one way is that at the beginning itself, you construct some large enough universe, and you're taking subsets only from that universe. So if you go back and if you notice, this is why at some point I notice that all subsets that I'm considering over here of points, they're subsets in subsets of X.
Yes, sir. Yes.
Right. So this is so sort of, I mean, the question that you're asking, the objection is a very valid objection, but I have simply I chickened out by means of the way I have defined what I mean by union and intersection here, right? Notice it's a colon equal to that's my definition of union and intersection.
Yes, sir.
Right. So
Yes, sir.
So, I mean, but this still begs the question. I mean, what is your set theory? What are your axioms of set theory? And, there are people who have done this. People do these things, even for research. People do research in set theory these days at some absurdly high level. But yeah, one has whatever the Zermelo-Frankel's colon set theory, right? Which working mathematicians, so to speak, sort of ignore, saying that, yeah, those people have worked out and we will just do whatever we want. But it's a valid question.
Yes, sir.
If you do not like what I have done over here, then you simply add that as extra condition. So maybe I can do this. That topological space with a collection of subsets of X, including the empty set and the whole space. You put that as part of the definition if you don't like this. Okay, anything else? All right, so we'll stop. We'll continue on Monday, and so you should get in touch with your TAs this weekend. I'll send a common mail to start the process. So expect that later today. All right, bye everyone.
Thank you, sir.
Thank you, sir. Bye, sir.